So here is a Doberman Pinscher. They have a temperament that is alert, obedient, loyal, energetic, fearless, and intelligent. These are good dogs. They're good. They're good dogs. Notice these words are descriptive, much like descriptive statistics, and also notice the lifespan of these things is given as an interval. Consider one of our topics in the course, a big one, is called confidence intervals. All right, so that's enough about Dobermans. Let's get rid of this. And, we're going to keep talking about Dobermans, but it's, it's like well, you can read the problem. You should. Just trying to get this out of here. There we go. Nope. There we go. All right, so the weight of these Dobermans follows a normal distribution. They're approximately normally distributed. All right? So it's interesting, I think, going from discrete probability distributions, which really are challenging, to we're basically going back over the empirical rule here. All right. So these can be a little bit tricky when you're working when you're trying to find some x value, but really nothing compared to Chapter 4, which is why there are so many problems with Chapter 4 that I wanted to throw at you for practice. Anyway, we have a random variable x. I'm going to set it red for the Doberman. X equals body weight. And x follows a normal distribution. And the notation we use for normal distribution, not that this is going to play a big role in our course, is the mean followed by the variance. I know, the variance, not the standard deviation. But anyway, that's not going to make a difference in this problem. The important thing to note here is that the mean is 75 and the standard deviation is 10, and we want to standardize the value 62.3. Standardize. So what that means is we want to figure out what percentage of Dobermans would be less than adult males, by the way. 62.3 pounds. An obnoxious value, but a purposeful obnoxious value, because no matter whether or not we land a whole number of standard deviations away, like the empirical rule, it no longer is necessary because we have the standard normal table. So we're going to convert to a z-score of the 62.3 pounds. And then we're going to find it on the curve and then shade if we want. So let's go ahead and do that. Zoom in right here. And then pull one of these. And then we have z equals the value that we want to standardize is 62.3. And then we're going to subtract the mean. So half of Doberman adult males are more than 75 pounds, half are less. And then we'll divide by the standard deviation. This will convert from pounds, Doberman pounds, to the universal, I like to say universal language of science, the z-score, the standard score. Down the road we'll see it called the test statistic. We'll also see it called the critical value. The z-score formula will come up over and over and over again. So our z-score here equals negative 1.27. So if you have a Doberman that weighs 62.3 pounds, well, give you some feedback on you and your Doberman. it doesn't weigh 62.3 pounds. Your scale just cut it off right there. Is a hint about number 2. Let me show you. Hint about number 2, but we'll get to number 2 in a moment. But let's set up our probability that we want to find, because we love showing our work. It's just what we want to do. We want to find really more so in this class so that you can develop the conceptual meaning rather than having it be any sort of extrinsic reward. Like, show your work. It's really a lot of independence is assumed. Okay, so the probability that a Doberman is less than 62.3 pounds. Nobody uses pounds except United States and United States people, right? That's it. But this has the same area. An area is probability. It's modeled as probability when we're dealing with normal models. It's the same probability as this probability. It's the same thing. It's just that with the standard normal, we have a table and the empirical rule, which would give a good approximation. The key here is we don't have to use integral calculus. So that's exciting for a lot of people. I don't think it's exciting. I think using calculus is good. At least once, but we're not going to. All you have to do is find negative 1.27 and then give yourself a little bit of room for a little sketcheroo. And how much stuff is in there? It is a point. If you use your table, it's about it's 10%. That's the answer. Now, number 2 is a little bit different. Different in that it's the easiest problem ever if you are aware of the fact that we are modeling a continuous random variable. And with a continuous random variable, we have a measurement. And I'll go ahead and zoom in here to show you that there are an infinite number of values between any 2 lines that I draw on this curve. So consider the following that I have, right? Your Doberman, you're like, hey, it weighs 62.3 pounds. Well, I don't care what number you put here for your weight of your Doberman. I will always find a Doberman that is heavier, and infinitesimally heavier. What values this little red line? I don't know. How about that 62.3000001 pounds? And then the idea being that there's not many Dobermans between. I do problems about greyhounds too. I keep wanting to say greyhounds, but there's not many, right? Practically, there's not that many in here. But also theoretically, because we're modeling as continuous data and as a measurement and area, a line, Euclid, the famous poet, said, a line is of breadthless width. Just kidding. Euclid was a geometer. That's what Wikipedia said. No, he was a Greek, really badass mathematician. But zoom in here. There's no area for a line. That's why all of our probabilities are pieces of area. Probability to the left, probability to the right. So the answer to number 2 is, let's see, number 1 is 10%. Number 2 is 0. So next time your friend says they have something that is measured, they said, my temperature is 102 degrees, 102.2 degrees. You say, no, it's not. And they say, I'm sick. You say, well, all right, but know that your temperature is not 102 degrees exactly. Keeps going on forever and ever, depending on how precise our measurement device is. But either way, definitely take your friend to the hospital.